differentiation. So the first section is called the basic integration rules. Actually, we are talking about this, integration by substitution specifically for this section. I think we covered the substitution and integration in Cal 1. But, you know, you get more complicated problems. So let's just talk about some examples that's really challenging. And you know, the substitution, integration by substitution is always the first rule you want to use whenever you have a problem to integrate. Okay, if you cannot get the answer right away, one step, then you consider integration by substitution. That's always the most important rule. Okay. So this is called the fitting integrals to basic rules. What it means is sometimes you get a problem that really doesn't look like you know, any formula in integration table. Then you try to rewrite the problem to fit the formulas. Okay. So in this specific problem, we try to carry out the integration of x squared over square root of 16 minus x to the 6th. Okay, so if you look at the integration table in the book, you will not find the formula for this. So as I said, you're going to consider integration by substitution. The integration substitution means that you need to define a new variable to solve the problem. Now, if you look at the function inside the integral, it's x squared over square root of 16 minus x to the 6th. So we got the square root in the denominator and something subtracts something. And then if you check the formulas in the book, in the integration table, then you find out one formula for this is the integral of 1 over the square root of a squared minus x squared. It's just arcsine of x over a plus c. That's from the integration table. Okay, so that really tells us, you know, we can match the problem with the formula in some way. So, you know, to match the problem with the formula, we need to rewrite the problem a little bit so that it looks like the formula. So let's just rewrite the problem as square root of 4 squared minus x cubed squared inside the radical in the denominator, because that's what it is in the formula. So fitting integrals to basic rules. All right. So that means, or that suggests us we need to use the substitution of u equal to x cubed so that we can rewrite the whole thing as 4 squared minus u squared inside the radical in the denominator, isn't it? And then we match the formula for the problem. Okay, so then just follow the standard procedure for integration by substitution once you start the substitution. So take the differential of u, you get du equals 3x. The derivative of x cubed is just 3x squared. And then divide by 3x squared on both sides. You got the dx equals du over 3x squared. And then you just plug that into the original problem and change everything in terms of u. Okay, so the integral becomes x squared over square root of 4 squared minus u squared, as I said. And then dx, you replace it as a du over x 3x cubed. Now you see x squared on the top and at the bottom that you can cancel. So then you're just left with 3 in the denominator that you can take out. So you get 1/3 times the integral of du over square root 4 squared minus u squared. And then you can use the formula, you know, integral of 1 over square root squared minus x squared equals arcsine x over a. So then we get 1/3 times arcsine u over 4. So here you it's u instead of x, but you just change the s later. Okay, later. And the a will be 4. All right. And it's not complete yet. You need to come back to the original variable x. So u is just the x cube as a substitution. So just replace back x cube for u, and you get 1/3 arcsine x cube over 4 plus c. Okay, this is indefinite integral. You got to see in here. Any questions for this particular problem? So let's call them fitting integrals to basic rules. It means you you see the problem and then you check the formulas in the in the book, in the table, and try to match the problem with one of the formulas. And then to do that, you need to rewrite the integrand of the function exactly the same way as it appears in the formula, right? And then you can apply the rule. Okay, so that's what it means. So no question, then I will do the next. Okay, in this problem, we need to carry out the integration of cotangent x times the ln sin x. Well, this looks very complicated, but again, if you look at the integration table, there's no formula for this kind of problem. So the first thing to consider is the substitution. So so we have different choices here. We can either use u equal to cotangent x or u equal to ln sin x. Which one will work? It turns out only substitution of u equal to ln sin x works, and the u equal to cotangent x will not work if we try it. So let's see how it works. Again, take a differential of u, you get 1 over sin x. Remember, then ln function, when you take the derivative, you get 1 over the argument. But because the argument, the sin x, is a function itself, you need to use the chain rule when you take the derivative. Okay, so we got the cosine x, that goes to the top. And so cosine x over sin x, that's the differential of u, which is cotangent x exactly, appearing in the integrand. So divided by cotangent x on both sides, so you can rewrite dx equals du over cotangent x. And then we can carry out the integration by replacing x with u for the substitution. So ln sin x is just u, so we get cotangent x times u, and dx is just du over cotangent x. So plug those in, and then you see you got cotangent x at the bottom, and on the top. In the first function is cotangent x, that means it's on the top. Okay, so then they cancel each other. So at the end, you just left the u and to integrate u du. So that gives you 1/2 u squared plus c. Okay, here u is the variable, so just use the power rule here, and then replace back ln sin x for u. You get 1/2 ln sin x squared plus c. So that's the answer. This problem looks really weird, but once you get it right, the substitution, it works out real quick. Any questions for this problem? Okay, no question. Then we go to the next one. All right. Okay, so this one turns out to be not very complicated. Just one example showing how to do trig integrals. I mean, this is usually this will be complicated, but for this particular problem, it's not very hard. So we need to integrate the tangent to x squared. Okay. Well, we have to use some trig identity. And here we just use the identity of tangent u squared equal to secant u squared minus 1. And then you can rewrite the integral as secant 2x minus 1. Okay. And then that becomes two integrals. One is secant 2x squared, and the other is just integrate 1. Okay, we know how to do that. To integrate secant 2x squared, you just again you have to use substitution here, but this time we just let u equal to 2x. Okay, so every time when you have some, constants or something, some coefficient with x, multiplying the x, you need to use substitution. Okay, always. So take the differential of u, you get du equal to 2dx, divided by 2 on both sides, you get dx equal to du over 2. And plugging that into the original problem, so we got secant 2x squared, just secant u squared, because u is defined as 2x. And dx is just du over 2, we just got it. And then minus the integral of 1 for x. So, you can take out half from the first integral is in denominator, so that's half. And the second you integrate, you get tangent if you look at the integration table, if you forget. And then integrate 1 over x, you get x, so that's minus x plus c. And then just write back u to x, so we got half tangent 2x minus x plus c. And remember, u is 2x as we defined in the substitution. So any questions for this sample? Not particularly hard. Okay, so that's the end of this section real quick. So let's go to the next section if you don't have any questions. Okay. I need to okay, I think I have it in here, so let's see, 8.2, all right. So in 8.2, we're going to introduce another important technique in integration. Remember, we have a bunch of rules in differentiation, but in integration, we don't have many tools, unfortunately. As I said, integration by substitution is always the first priority to use when you don't find the answer directly from the formulas. If that doesn't work out, then the next thing you try is integrating by parts. Those are the two most important techniques in integration. Okay. So how does it work by integrating by parts? Okay, this is from okay, skip the first page. From the product rule in differentiation, suppose you have two functions u and v, and you want to take the derivative of the product of u and v. You use the product rule. So you take the derivative of u and times v plus the derivative of v times u. Okay, I just wrote it backwards, but that's what you do. Okay, then you integrate on both of this formula of this rule. You can get the u times v on the left, because when you take the derivative of u times v and then integrate, you should get u times v back from the fundamental theorem of calculus. All right. On the right side, you got two terms, u dv plus v du, two integrals. How did you get that? Because when you integrate u times v prime, okay, dv over dx, that's v prime. You got v prime dx. That is exactly dv. Remember, the differential of v is just v prime times dx. Okay. Similarly, du over dx is u prime, and the u prime dx is just du. Okay. When you integrate, that's the differential of u. So now rewrite this by you know separating the integral udv on the left, and then on the right you're going to get u times v minus the integral of v du. So this is the formula for integration by parts. So it looks a little weird because it's not usually what we see in integrals. We have potential for u and the v, the functions. And that's the way it is. And when you actually apply this method in problems, it does work in that way. Okay. So let me just rewrite this formula on the next page. The integral of u dv equals uv minus the integral of v du. Okay. So why do we need this formula, and how does it work? In many cases, you try to integrate u dv. Okay, you can rewrite the problem as the format of UDV. In the problem itself, it doesn't give you this format. It's just the X for everything. But you can rewrite the problem as UDV, as we will see later. Then it will be hard to integrate it directly. Then you try to change to this integral into the one on the right, which is uv minus the integral of v du, and you might be able to solve the problem easily. Okay, so you change the integral in this way. So let's just start from an easy example of integral by parts. This method. So we need to integrate the x times e to the x, and you cannot find any formula in the book to get the answer directly, or there's nothing to substitute. You cannot define any new variable in here. So integration by substitution doesn't work in here. So then you have to try integration by parts. Now, in this problem, we got the x times ex times dx. So this is the whole thing of udv. If you want to use the integration by parts, then this is the left side, okay, in the form. So then we need to identify this, x, ex, dx. Which one is u and which one is dv, all right? So it turns out in this problem, you can define u to be x and the dv to be e to the x dx. Remember, that's the whole point of differential, okay? So you have to include everything, including dx in the problem. And then what you do is you need to take the differential of u because u is just x, so du is just dx. To get a v, you just integrate e to the x, and you get e to the x itself, okay? So then using the formula for integration by parts, so udv, integral of udv, which is x, e to the x dx, is equal to uv minus the integral of v du. So plug in u and v in here, so u is x and v is e to the x. So we get the x times e to the x in the first term, and minus the integral of v du. Now v is e to the x and du is dx. So we got the integral of e to the x dx in the second term, and that just gives us e to the x if we integrate it. So the final answer is just the x e to the x minus e to the x plus c. So you can see how that works. So let's just do some more examples if you still have don't have any idea of how it works. Okay. Let's see. Page 3. So I always put the formula in the pages in case you forget. So we need to integrate x squared times ln x dx. Again, you cannot find the formula in the book, in the integration table. So then, and there's nothing to use substitution, integrate by substitution. If you try to define u to be ln x or x squared, they will not work if you try it. So then we have to try integration by parts. So again, the whole thing x squared and x dx will be u dv in our problem. And then you need to identify which one is u and which one is dv in this problem. So we only have two functions, x squared and ln x. So which one is the u? Okay, remember u and v are both functions of x. And it turns out this time you can only choose u to be ln x to work it out. If you choose u to be x squared, it will not work. So let u equal to ln x and dv equals x squared dx. So the remaining part, if you take out ln x, and then the remaining part is just x squared dx, and that's the dv in the formula. Okay, so then you take the differential of u, you get du equals 1 over x, which is the derivative of ln x times dx. Okay, the differential. And to get the v, you just integrate x squared, get 1/3 x cubed. So now the problem becomes, x squared and dx equals u dv, and use the formula for integrating by parts. You get the uv minus integral of v du, and plug in u and v and solve the problem. So u is just ln x. Okay, so v is 1/3 x cubed. So plug in, you get the ln x times 1/3 x in the first term, and then subtract the integral of v du. V is 1/3 x cubed, and the du is 1 over x dx. We got in the previous step. Now, in the second term, the integral, you can simplify this a little bit by canceling x in here. So you're left with x squared. And you can take out 1/3 from the inside of the integral. So that becomes 1/3 x cubed ln x minus 1/3 x squared dx. It's not d, it's dx. Okay, it's type on here. So now that's easy to integrate. X squared integrate, you get 1/3 x cubed. So the whole thing is just 1/3 x cubed ln x minus 1/3 times 1/3 x cubed plus c, and that's just the 1/3 x cubed ln x minus 1/9 x cubed plus c. Okay, so again, the integration by parts works. Any questions at this point? No questions, then just continue. One more problem. Okay, so again, you can see the formula on the top. This time we need to integrate the problem at definite integral. Okay, it's essentially the same steps, but you have one more step at the end to plug in numbers. When you get the antiderivative and then subtract, right? Okay, so again, we got the arc sine x dx, then that should be u dv in our problem. If you check the integrand table, you don't see the formula, and if you try to use integrand by substitution to define new variable, it will not work. Okay, if you try that. So we only have one function arc sine x in here, so that has to be the u if you try to use integrating by parts. Okay, and then the other part, the dx, it must be dv, right? So very simple in this case, no choice. So then you take the differential of u, you get 1 over square root of 1 minus x squared. That's the derivative of arc sine x, and times dx, the differential. And to get the v, you just integrate dx, which means you integrate 1, so you get x. So now you can plug in the formula for integrating by parts and then carry out the integral. So we got arc sine x dx from 0 to 1 equals u dv for the 1, which is uv minus the v du. And then u is arc sine x, so that's arc sine x, and the v is x, so you have to multiply x by that. And then you need to evaluate this function at 0 and 1, subtract. Okay, that's a definite integral. And the minus the integral from 0 to 1 for v, which is x, and the du, which is 1 over square root of 1 minus x squared dx. So we need to integrate that. I just rewrote the second term to put x on the top, which is what it means in this product inside the integral. Okay, so now we need to do the second integral. And now you can use substitution to do the problem. It will be real straightforward. Okay, so I just rewrote the result from last step in the previous page again on the first line here. So the arcsine x from 0 to 1 is just the arcsine x times x from 0 to 1 minus the integral of x over square root of 1 minus x squared from 0 to 1. Now, use substitution as I said. You just let u equal to 1 minus x squared. The part inside the radical in the denominator, and it will work out. Follow the standard procedure of integration by substitution. Take a differential, you get du equals negative 2x dx. Okay, the derivative of 1 minus x squared is just negative 2x. And divide by negative 2x, you get dx equals du over negative 2x. All right? And then you should figure out the new lower and upper limits of integration for the new variable u. So when x is 0, u will be equal to 1 minus x squared, so that will be 1 minus 0 squared, which is 1, isn't it? When x is 1, u equal to 1 minus x squared, so you subtract 1 minus 1 squared, so you get 0, okay? So the integral of x over square root of 1 minus x squared from 0 to 1 becomes the integral of u from 1 to 0. When x is 0, u is 1. So you get 1 in the lower limits of integration. And then when x is equal to 1, u is 0. So you get 0 at the upper limit of integration for u. Okay? So, and then what? Then you get the x on the top and the square root of u at the bottom, because u is just the 1 minus x squared, remember? And then dx is just the negative d over 2x as we already did. And then you can see x cancels in the problem inside the integral. And then you can take out negative half from inside and to get the 1 over square root of u inside. And that will be easy to integrate if we rewrite square root of u as u to the half and then change it to negative exponent because it's in the denominator. Okay, so you get u to the negative half to integrate it, and that gives you u to the negative half plus 1 over negative half plus 1 using the power rule. You still get negative half in the front, by the way. So that's negative half u to the half over half, and negative half plus 1 is half. Simplify this a little bit. Half and half cancels, so it becomes negative u to the half from 0 to 1. So what you do is just plug in 0 and 1 in u and subtract. So you get the negative 0 to the 1 half minus negative 1 to the half. Okay, so you get 0 in the first term and you get the 1 from 1 to the half. And there's two negative signs in here, so it becomes plus 1. Okay, so at the end you get 1. So that's the whole thing for the second term in the original problem, the integral of x over square root of 1 minus x squared from 0 to 1. So then we just go back to the original problem and to get arcsine x times x from 0 to 1 minus 1. Okay, and we just got that whole thing in the second term to be 1. For the first term, you plug in 1, 0, so you get the arcsine x, it should be arcsine 1, okay, I'm sorry, times 1 minus arcsine 0 times 0, again, it should be arcsine 0. Arcsine 1 is just power 2 times 1, so you get power 2, and the arcsine 0 times 0 just 0. So at the end, you still need to subtract 1, okay, from the original problem. So you get power 2 minus 0 minus 1, so that's power 2 minus 1. So that's the answer. Any questions? So it takes a little more steps to do the definitely you still need to evaluate, the lower and the upper limits of integration. But for this particular problem, because we we need to use substitution to figure out the second term of the integration, x over square root of 1 minus x squared. So it's a little lengthy. All right. Any questions so far? No question. Then we go to the next page. All right. So let's do one more problem. Okay. This time I'm going to integrate x squared with times sine x dx. Okay. So this will be u dv again. Identify u and the dv here, and it turns out we can choose u to be x squared and dv to be sine x dx. Again, if you choose u to be sine x and dv to be x squared dx, it will not work out. Okay, you can try it. So for the standard procedure, by taking the differential of u, you get 2x dx. X squared take derivative is 2x. And to get the v, you just integrate sine x to get the negative cosine x. So that's just the v. So we got the integral of x squared sine x dx rewrite as u dv. So that's uv minus integral of v du according to the formula for integration by parts. And plug in u and v in this formula, you get the x squared, which is u, and the negative cosine x, which is v in the first term, minus the integral of v, which is negative cosine x, and du, which is 2x dx. Okay, you have to use the formula exactly as it appears. So we got a negative x squared times cosine x, and plus the integral of 2x cosine x. You can take out 2 from the inside of the second integral. So we still need to integrate x times cosine x. So it turns out that we have to use the integration by parts one more time to figure out this second term. Okay, so let's do that. So again, I just rewrite the results we got from previous page. Square sine x integral of that equals negative x squared cosine x plus 2 times the integral of x cosine x. As I said, we have to use integral by parts one more time to figure out the integral of x times cosine x. Okay, so again, you're going to use u equal to x and dv equal to cosine dx, cosine x dx. And it will not work if you choose the other way, u equal cosine x and v equal to x dx. It will not work. So then you take a differential of u, you get it du equal to dx, and integrate the cosine x, so you get a v, so that's sine x. So now the integral of x cosine x just rewrite as u dv, which is u minus the integral v du according to the integration by parts. So plug in x for u and the sine x for v. We got the x sine x in the first term minus integral of v du, which is sine x dx. You know, that would be easier to integrate sine x. You get the negative cosine x. You get x sine x minus the negative cosine x. So that becomes x sine x plus cosine x plus c1. So you do get the constants from here, arbitrary constant. So the original problem is just x squared sine x dx. Integrate that is negative x squared cosine x plus 2 times integral of x cosine x. If you look at the first line on this page, okay, we have figured out the second term here on this page. Just plug in the integral of x cosine x, which is x sine x plus cosine x plus c1. Okay, so that becomes the negative x squared plus times cosine x plus 2 times x sine x plus cosine x plus c1. So distribute 2, you get the negative x squared cosine x plus 2x sine x plus 2 cosine x plus 2c1. And you can rewrite the 2c1 as c. That's just the arbitrary constant. So the final answer would be negative x squared cosine x plus 2x sine x plus 2 cosine x. So let's just do one more problem to finish this section. Okay, integration by parts. this time we need to carry out the integral of secant x cubed. Again, you cannot find the answer directly from the formulas or use substitution. They will not work. Okay, if you try to substitute the u to be secant x, it will not work out. So then you try to use integral by parts. Then you need to have u and the dv in this problem. It turns out that you need to rewrite the problem a little bit by breaking secant x cubed as secant x times secant x squared. Then you have a choice for u and the dv, and that will work out. Okay, so that's a small trick in here. So let's just define u to be secant x and dv to be secant x squared dx. Take the differential of u, get a secant x, tangent x dx. You take a derivative secant x, get a secant x of tangent x. Okay, I will finish this problem real quick and take the rule, and then you can leave. Okay, and integrate secant x squared, you get a tangent x, so that will be v. So now plug into the formula. So secant x cubed, you can rewrite as u dv, and as uv minus integral of v du. So plug in u secant x and v tangent x, you got secant x tangent x minus the integral of v du. So that's tangent x times secant x tangent x dx. So you get a secant, yes, I understand. Okay, it'll be quick. Okay, so that will be secant x tangent x minus secant tangent x squared. Okay. Now we have to use the formula again here. Okay, so I just rewrote the result from the last page. Secant x cubed equal to secant x tangent x minus secant x tangent x squared. We got on the last step. Using the identity of tangent x squared equal to secant x squared minus 1 in the second term on the right inside the integral. So we got the secant x cubed dx integral of that equals secant x tangent x minus secant x squared minus 1, which is the tangent x squared. And then distribute the secant x in the integral. We got two terms, so it becomes secant x tangent x minus the integral of secant x cubed plus integral of secant x. And the original problem was it's just two, if you look at the left side and the right side, okay, then you can combine the secant x cubed on both sides. If you add it, one secant x cubed integral on both sides, so you get 2 times the secant x cubed on the left, and on the right is secant x tangent x plus the integral of secant x, and you can find the divided by 2, then you get the answer of secant x cubed. The integral of that equal to half of secant x tangent x plus the integral of secant x. The integral of secant x, you can find it from the book, the formula. So that's just the natural log of absolute secant x plus tangent x. So at the end, the answer is half of secant x tangent x plus the ln of secant x plus tangent x. Absolute of that plus c. So that's the end of this section.